A modern gun hides almost everything that makes it work. Pull the trigger, and the important events happen inside metal. A small ignition begins. A chemical propellant turns solid material into expanding gas. Pressure rises. A projectile accelerates through a tube. In a fraction of a second, chemistry becomes motion. The strange part is not that humans learned to build this machine. The strange part is how long it took them to realize what they had. Because the first people to make gunpowder were not trying to invent guns. The earliest guns were not especially accurate. They were slow to reload, vulnerable to rain, dangerous to their users, expensive to manufacture, and surrounded by older weapons that experienced soldiers could often use more effectively. Yet guns survived. Then they multiplied. Eventually, they changed castles, armies, factories, empires, hunting, policing, politics, and the relationship between an ordinary person's finger and lethal force. There was no single moment when somebody invented the gun. Instead, humans had to solve a sequence of separate problems. First, they needed a substance that released energy rapidly. Then a container strong enough to confine that energy. Then a way to direct it. Then a projectile that sealed the tube well enough to capture the pressure. Then a reliable method of ignition. Then a way to reload faster. Then a way to manufacture thousands of weapons whose parts and ammunition behaved predictably. The modern gun is the result of all of them. And the story begins with people who were searching for something almost exactly opposite to a weapon. They were looking for immortality. During the first millennium CE, Chinese experimenters working within alchemical traditions investigated minerals, salts, metals, and combustible substances in attempts to transform matter, and in some cases, extend human life. Among the substances they studied was saltpeter. Saltpeter behaves strangely around fire. It supplies oxygen to combustion. Combine it with the right combustible materials, and fire no longer depends only on oxygen arriving from the surrounding air. The reaction can become dramatically faster. That discovery produced what Europeans would later call gunpowder. The surviving evidence does not identify one inventor. Nor can we place a finger on one afternoon when the mixture suddenly appeared. Chinese texts suggest that knowledge accumulated through generations of experimentation. By the 9th century, writers were warning about mixtures capable of violently burning hands, faces, and buildings. That warning tells us something important. The chemistry came before the weapon. In 1044, the Chinese military work known as the Wujing Zongyao recorded several gunpowder formulas and described military uses for gunpowder mixtures. These early compositions were not simply modern ammunition waiting to be placed inside a gun. Gunpowder technology itself was developing. At first, its most obvious military property was fire. So armies attached incendiary mixtures to arrows. They made burning devices. They developed bombs and explosive containers. They experimented with ways to frighten enemies, ignite wooden structures, and disrupt formations. None of that required a gun. The missing idea was confinement. Set gunpowder on an open surface, and much of its expanding gas escapes in every direction. Put it inside a tube with one open end, however, and the same expanding gas has fewer places to go. Now place something in front of it. The pressure pushes that object toward the opening. That is the fundamental physics of a firearm. The gun is not really a device for making an explosion. It is a device for controlling expanding gas. Once that distinction was understood, a weapon that began almost like a flamethrower could slowly become a gun. Chinese soldiers developed weapons now called fire lances. Early versions were essentially tubes attached to shafts or spears. When ignited, the tube blasted flame, hot material, smoke, and eventually fragments toward an opponent at close range. Imagine the effect in a medieval fight. There is noise, smoke, burning particles, a violent flash directly in front of your face. It does not have to be accurate at 100 meters. It only has to make you hesitate from 3. But someone eventually discovered that the blast could do more than throw flame. Put a solid projectile inside the tube, and the expanding gas could launch it. At that point, the fire lance begins to cross an important technological boundary. The gunpowder is no longer merely burning the enemy. It is providing the energy that throws something at them. The spear has acquired an engine. The next problem was the barrel. Bamboo works for a fire lance because it is lightweight and cheap. It is less attractive when pressure rises. Stronger propellant and tighter projectiles create more force, but that force pushes in every direction, including against the walls of the tube. If the barrel fails, the gun fires inward. Metal changed the equation. Bronze and iron could contain much greater pressure. By the late 13th century, China possessed true metal-barreled firearms. One of the best-known surviving examples is the Heilongjiang hand cannon, a small bronze weapon associated with fighting in the 1280s. It does not look much like a modern rifle. There is no elegant trigger, no magazine, no shoulder stock in the modern sense. It is essentially a sturdy metal tube designed to survive an internal blast and send a projectile out of one end. But that tube contains the central idea of every conventional firearm that followed. Combustion behind, projectile ahead, one exit. The invention was already complete in principle. In practice, almost everything still needed improvement. And then the technology began moving. The 13th century was an age of enormous Eurasian contact. Mongol conquests linked regions that had previously interacted less directly, moving soldiers, artisans, administrators, merchants, technologies, and information across extraordinary distances. Historians continue to debate the precise routes through which particular gunpowder techniques spread. But by the early 14th century, firearms appear clearly in European records. Florentine documents from 1326 refer to metal cannon. An English manuscript from roughly the same period illustrates a pot-shaped gun firing a large arrow-like projectile. Europeans had entered the experiment. At first, the gun was not replacing the sword, bow, or crossbow. It was joining them. A medieval army might contain archers, spearmen, armored cavalry, crossbowmen, engineers, and men serving primitive artillery. Each technology solved a different problem. The first problem guns solved spectacularly was not how to hit a moving soldier. It was how to hit a wall. A wall does not dodge. For centuries, medieval rulers had poured wealth into vertical defenses. Stone castles rose high above the landscape. Towers projected from walls. Attackers used ladders, mining, siege engines, blockade, starvation, and enormous patience. Early cannon were awkward. They could weigh tons. Moving them required animals, wagons, roads, crews, and money. Firing rates were painfully slow. But a cannonball could deliver repeated impacts to exactly the same piece of masonry. And artillery improved. By the 15th century, large guns were changing the economics of fortification. Walls that had represented generations of security could now face sustained bombardment from weapons that rulers could move from siege to siege. The symbolism was almost as important as the physics. A castle concentrated local power. A noble family might fortify one place and dominate the surrounding countryside. Heavy artillery concentrated a different kind of power. To buy metal, employ founders, transport guns, manufacture powder, feed crews, and maintain arsenals required deep resources and organization. Guns did not automatically create centralized states. History is rarely that clean. But increasingly, serious artillery favored rulers who could collect taxes and coordinate specialists on a large scale. The weapon was becoming an institution. The Siege of Constantinople in 1453 became the most famous demonstration. Ottoman Sultan Mehmed II brought an army equipped with gunpowder artillery against walls that had protected Constantinople for centuries. Some of the Ottoman bombards were enormous, yet it would be misleading to say one giant cannon simply knocked down the Byzantine Empire. The siege involved artillery, infantry assaults, naval operations, engineering, logistics, and relentless pressure. That matters because it reveals the real advantage of the gun. The machine alone was never enough. A cannon without powder is a metal pipe. Powder without transport is stored energy in the wrong place. A gun without trained crews may be more dangerous to its owners than its target. Firepower only becomes power when an organization can keep feeding it. The Ottoman military became exceptionally good at doing that. Artillery specialists and firearm-equipped troops were integrated into a permanent military system. The Janissaries, among the most famous infantry formations of the early modern world, adopted firearms alongside older weapons. The lesson spread. Across Eurasia, states adapted gunpowder technology to very different military traditions. The Safavids, Mughals, European kingdoms, Chinese dynasties, Southeast Asian polities, and later Japanese armies did not simply receive a finished invention from one source. They modified guns according to local materials, enemies, tactical needs, and manufacturing traditions. Japan offers a remarkable example. Portuguese-linked firearms arrived there in the 16th century, traditionally associated with Tanegashima in 1543. Japanese craftsmen did not merely import the weapons indefinitely. They studied them and began producing matchlock guns locally. That distinction is crucial. Technology becomes historically transformative when knowledge can move from owning an object to reproducing the process that makes it. Once gunsmiths understood the barrel, lock, stock, projectile, and ignition system, the firearm was no longer foreign cargo. It was an industry. But the handheld gun still had an embarrassing problem. Using one was clumsy. An early hand cannon might require the shooter to hold or support the barrel while bringing a burning match or hot wire toward an ignition hole. Try aiming carefully while also manually introducing fire to the weapon you are holding. Not ideal. The matchlock turned ignition into a mechanism. A slow-burning cord was held in a movable arm. Pulling a lever or trigger lowered the glowing match toward priming powder. Now the shooter's hands could support and aim the gun while the mechanism managed the final step. It sounds modest. It was enormous. The trigger separated aiming from ignition. Once that happened, the firearm began becoming a true personal machine. Shoulder stocks improved control. Sights helped alignment. Barrels became more consistent. Powder quality improved. Soldiers learned coordinated loading procedures. Still, a skilled archer had serious advantages. A good bow could fire repeatedly. It did not fill the battlefield with smoke. It did not depend on a burning cord. It was far quieter. Under the right conditions, an experienced archer could place arrows with impressive precision. So why abandon bows? Because military technologies are not judged only by the best person using them. They are judged by systems. Producing an expert military archer could require years of physical conditioning and constant practice. A firearm shifted much of the projectile's energy away from the soldier's muscles and into stored chemistry. The shooter's body still mattered. Discipline mattered enormously. Marksmanship could become highly skilled, but the source of launch energy was standardized. A smaller recruit and a stronger recruit could fire broadly similar projectiles from broadly similar weapons. Training increasingly focused on repeatable procedures: load, prepare, present, fire, reload. The gun transferred part of military skill from the body into the object. That made drill extraordinarily valuable. One soldier reloading is vulnerable. Rows of soldiers coordinating their actions can maintain repeated fire. Commanders experimented with ranks, rotations, formations, and combinations of firearms with pikes or other weapons. The gun became effective not simply because one bullet was devastating. It became effective because hundreds of people could be synchronized around it. This is where the history of firearms becomes a history of labor. Somebody had to make the barrels. Somebody had to cut stocks. Somebody had to manufacture locks. Somebody had to extract and refine the ingredients for powder, cast projectiles, transport supplies, repair damaged weapons, inspect stores, keep powder dry, and move ammunition toward armies that consumed it continuously. A sword can remain useful for years with maintenance. A firearm is hungry every time it works. Its power depends on a supply chain. That hunger helped states build arsenals and workshops. It encouraged standard sizes and procedures. It also created dangerous industries in which workers handled combustible material, heavy metal, toxic lead, hot furnaces, and machinery. The spectacular moment is the shot. Most of the history happened before the trigger was pulled. Meanwhile, cannon forced another transformation. High, thin medieval walls were vulnerable to improved artillery, so military engineers began building defenses lower and thicker. Earth absorbed impact better than brittle vertical masonry. Angular bastions allowed defenders to fire along approaches to the walls. Across parts of Europe, the outlines of fortified cities changed. From above, many began resembling stars. The gun had altered architecture. And those new artillery fortresses were expensive. Capturing them required larger engineering operations, trenches, batteries, supplies, and long sieges. Defending them required garrisons and maintenance. So artillery created an arms race between destruction and construction. Build a stronger gun. Build a thicker wall. Move the gun closer. Extend the bastion. Dig another trench. Raise another tax. Technology was pulling finance behind it. Handheld firearms were undergoing their own arms race against unreliability. The matchlock's glowing cord was an obvious nuisance. It could betray a soldier at night. Wind caused trouble. Damp weather caused more. Carrying an exposed source of fire near loose gunpowder produced additional excitement that nobody needed. More complicated wheellock mechanisms generated sparks mechanically but were expensive. Then, during the early 17th century, the flintlock emerged in Europe and provided a simpler long-term solution. A piece of flint struck steel. The impact produced sparks. Those sparks ignited priming powder, which transmitted fire to the main charge. No permanently glowing cord was required. Flintlocks became the dominant ignition system for military firearms in much of Europe and its empires for roughly 2 centuries. They were not perfectly reliable, but they were reliable enough. That phrase describes many successful inventions. Once an imperfect technology becomes dependable enough, the next revolution often comes from simplifying everything around it. Consider the infantry musket of the 18th century. By modern standards, it was not a precision rifle. Most military muskets had smooth barrels. The projectile did not engage spiral grooves that forced it into a stabilizing spin. Soldiers were often expected to fire as part of formations rather than act as isolated long-range marksmen. But the musket fitted a larger system beautifully. Paper cartridges could package a measured powder charge with a projectile. Drill manuals divided loading into standardized movements. Armies practiced those movements until large formations could perform them together. Then came the bayonet. Now the same infantryman who carried a firearm could also present a spear-like point from the muzzle. Separate formations of dedicated pikemen gradually became less necessary in many armies. A soldier was becoming a standardized weapons platform. That development carried a political price. Early modern warfare demanded enormous quantities of money, material, and people. States expanded taxation, borrowing, procurement, arsenals, and bureaucracy, partly to support warfare on this scale. Guns did not invent the modern state, but modern states and guns grew up together. And wherever those states expanded overseas, firearms entered histories of conquest, trade, resistance, slavery, and colonial rule. It would be equally wrong to imagine guns as a magical European advantage that automatically defeated anyone without identical weapons. Many societies acquired firearms quickly. Others already possessed them. Local alliances, disease, naval power, horses, population, logistics, internal rivalries, and political organization could matter more than any single gun. Firearms changed the balance. They did not erase everything else. By the late 18th century, however, another problem was becoming difficult to ignore. The gun was still slow to load, especially from the muzzle. Rifling had existed for centuries. Spiral grooves inside a barrel could make a projectile spin, improving stability and accuracy. But early rifles were often slower to load because the projectile needed a tighter fit against the grooves. That created a trade-off: accuracy or loading speed. Military systems usually wanted both. The 19th century attacked that compromise from several directions at once. First came better ignition. In 1807, the Scottish clergyman and experimenter Alexander John Forsyth patented an early percussion ignition system using a shock-sensitive chemical compound. Later percussion caps made the idea smaller and more practical. Instead of depending on sparks falling into an open pan, the shooter could use a compact, impact-sensitive primer. Rain became less troublesome. Ignition became more reliable. The gun was getting closer to being sealed. Then came a clever projectile associated with the Minié rifle system. Its design allowed a bullet to load relatively easily down the barrel, but expand when fired so that it engaged the rifling. Suddenly, infantry weapons could combine much of the loading practicality of the old musket with much greater useful accuracy. The effects were grim. During conflicts such as the American Civil War, increasingly accurate rifled shoulder arms encountered tactics that had evolved in an earlier technological world. Soldiers still marched and fought in dense formations, but the distances over which they could be hit had increased. Weapons can improve faster than doctrine. People pay during the gap. But muzzle loading itself was approaching the end of its dominance. Why put everything down the long front of the barrel when the rear could open? Breech-loading weapons allowed the shooter to load near the chamber. The idea was old, but making a breech strong enough to contain gas reliably had been difficult. Precision manufacturing helped solve it. So did the cartridge. For centuries, firing a gun meant managing separate components: powder, projectile, primer, tools. Paper packaging reduced some of the inconvenience, but the pieces still had to become one functioning charge inside the weapon. The self-contained metallic cartridge changed the architecture. Primer, propellant, projectile, and container, could travel as one unit. Insert it. Close the action. Fire. The metal case also helped seal the breech when pressure rose. A gun had become much easier to feed. That opened the door to repetition. Revolvers placed several chambers around a rotating cylinder. Lever action and other repeating mechanisms stored multiple cartridges. Bolt-action rifles eventually combined strong locking systems, magazines, and reliable metallic ammunition. The old cycle of individually measuring loose powder was disappearing. Ammunition became an industrial product. And this is where another invention, often overlooked in firearm history, became just as important as the trigger or cartridge. Interchangeability. For most of history, a gun was partly an individual object. Skilled artisans fitted components by hand. If one complicated part broke, a replacement might require filing and adjustment because no two weapons were precisely identical. Military governments hated this problem. They wanted thousands of guns. They wanted spare parts. They wanted inspectors to determine whether a component was acceptable without depending entirely on one master's judgment. During the 19th century, state arsenals and private manufacturers developed increasingly sophisticated machine tools, gauges, fixtures, and production systems to make parts to consistent dimensions. Springfield Armory and other American manufacturers played important roles in this transition. Samuel Colt's factories later became famous for combining specialized machinery, division of labor, inspection gauges, and large-scale production. The gun helped teach factories how to make machines out of standardized pieces. And those manufacturing methods escaped the gun industry. Workers and engineers carried knowledge into sewing machines, bicycles, agricultural machinery, and eventually automobiles. A technology built for warfare helped refine techniques used to manufacture ordinary life. Then black powder itself became the limitation. Fire a black powder weapon, and it produces smoke and fouling. On a battlefield, repeated firing can create a haze that obscures targets and reveals positions. In the 1880s, smokeless propellants transformed firearms again. French chemist Paul Vieille's poudre bee was adopted with the Lebel rifle in 1886. New propellants produced less smoke and allowed more powerful firearm designs. By the end of the 19th century, the essential architecture of the modern military rifle had arrived. A metal barrel. Rifling. Reliable primer. Self-contained cartridge. Smokeless propellant. Breech-loading action. Magazine. Machine-made components. None had been invented together. That is the point. The gun was assembled across centuries. One generation discovered energetic chemistry. Another put it in a tube. Another strengthened the tube. Another created mechanical ignition. Another improved the stock. Another cut spiral grooves. Another redesigned the projectile. Another sealed the ammunition into a cartridge. Another built machine tools capable of producing thousands of matching parts. No inventor could see the finished system from the beginning. And the most consequential breakthrough may not have been any single mechanism. It was scalability. The earliest gunpowder experiment was chemistry. The fire lance was chemistry attached to a spear. The hand cannon was chemistry trapped inside metal. The matchlock connected chemistry to a trigger. The musket connected the trigger to drill. The cartridge connected the gun to a factory. Interchangeable parts connected the factory to mass armies. At every stage, another piece of human organization became wrapped around the weapon. That is why the question who invented the gun is almost impossible to answer with a name. Chinese alchemists helped discover the chemistry. Song military specialists weaponized it in several forms. Chinese gunmakers developed the earliest known firearms. Technologies moved across Eurasia. Metalworkers, founders, soldiers, Ottoman artillerymen, Japanese gunsmiths, European lockmakers, chemists, machinists, state arsenals, and industrial factories kept solving different weaknesses. The gun was not one invention. It was a chain of inventions that learned how to cooperate. And there is a darker paradox buried inside that achievement. Humans spent centuries making guns easier to use. A hand cannon demanded awkward handling. A matchlock demanded fire. A flintlock demanded a sequence of practiced motions. A muzzle loader demanded time. Loose powder demanded care. Hand-fitted parts demanded skilled repair. Innovation removed those obstacles one by one. Ignition became enclosed. Ammunition became self-contained. Loading moved to the breech. Multiple cartridges could wait inside the weapon. Parts became replaceable. Propellant stopped filling the shooter's view with thick smoke. The machine required less negotiation from the person holding it. That is technological progress in the strict engineering sense. It is also what makes the history unsettling. Because every improvement that made a gun more reliable, faster, cheaper, or simpler also reduced some friction between intention and violence. The same human talent that makes tools convenient does not change character when the tool is a weapon. So how did humans invent guns? Not because somebody wanted a pistol and suddenly imagined one. They began by discovering that certain mixtures could store chemical energy. They learned to confine the expanding gas from that reaction inside a tube. They used the pressure to launch projectiles. They replaced fragile tubes with metal. They created mechanisms that allowed one person to aim and ignite a weapon more reliably. Armies wrapped those machines in drill and logistics. States built arsenals capable of feeding them. Engineers improved barrels and projectiles. Chemists improved ignition and propellant. Factories turned separate powder, primer, and shot into standardized cartridges, and turned individually fitted weapons into repeatable industrial products. The object followed the system, and the system followed the chemistry. That is why the history of the gun begins not with a gunsmith, but with experiments in substances made more than 1,000 years ago in China. People searching through nature discovered that matter could hold violence inside itself. For centuries afterward, human beings worked on the same problem: how to release that energy more predictably. Today, the result can fit inside a hand. Metal, chemistry, pressure, precision. A short mechanical sequence containing a very long human history. And behind every shot is the same ancient discovery. Fire does not have to stay where it starts.